Hello everyone, and welcome to this presentation on long short-term memory networks, or LSTMs. Today we're going to explore how LSTMs help computers understand sequential data like text, speech, and time series information. By the end of this talk, you'll understand how LSTMs work, why they're necessary, and what challenges we face when using traditional recurrent neural networks. LSTMs are one of the most important architectures in deep learning, especially for natural language processing and sequence modeling tasks. Let's get started. Let's begin by understanding what makes LSTM special. LSTM is a specialized RNN architecture that was designed to address the fundamental limitations of standard recurrent neural networks. First, LSTMs can remember long-term dependencies through an internal memory cell. This is crucial because many real-world sequences require understanding context from far back in the sequence. Second, they control information flow using sophisticated gating mechanisms. These gates act like valves that decide what information to keep, what to forget, and what to output. Third, and most importantly, LSTMs solve the vanishing gradient problem by maintaining a constant error flow through the cell state. This allows the network to learn from events that happened many time steps ago. Finally, LSTMs learn automatically when to remember and when to forget information, making them incredibly powerful for sequence modeling. Now let's compare standard RNNs with LSTM networks to understand the key differences. Looking at the structure, a standard RNN has just a single TAN layer and its repeating module. In contrast, an LSTM has 4 interacting layers, 3 gates, plus the cell state mechanism. In terms of memory, standard RNNs only have short-term memory. They struggle to remember information from more than a few time steps back. LSTMs, however, maintain both short-term and long-term memory through their dual-state mechanism. The gradient flow is where the real difference lies. In standard RNNs, gradients vanish exponentially over long sequences, making it nearly impossible to learn long-range dependencies. LSTMs maintain stable gradient flow through what we call the cell state highway. Of course, this comes with a trade-off in complexity. Standard RNNs are simple and fast, while LSTMs have more parameters and are slower to train. However, for most real-world applications requiring long-term dependencies, this trade-off is well worth it. Let's dive deeper into the LSTM's core concept, the memory cell. The LSTM cell maintains 2 types of state that work together. First, there's the hidden state, denoted as H_T. This acts as the short-term working memory. It's passed to the next time step and also serves as the output of the cell. You can think of it as what the LSTM is currently thinking about. Second, there's the cell state, denoted as C_T. This is the long-term memory and represents the critical innovation of LSTMs. It acts as an internal information highway that runs through the entire sequence. The cell state is what makes LSTMs so powerful. It flows horizontally through time, with only minor linear interactions, allowing gradients to propagate without vanishing. This is sometimes called the constant error carousel. Information is added to or removed from the cell state through 3 carefully designed gates, which we'll examine in detail in the following slides. Now let's look at the components that make up an LSTM cell. An LSTM cell consists of 3 sigmoid gates that control the flow of information. The forget gate decides what information from the previous cell state should be thrown away or kept. The input gate decides what new information should be stored in the cell state. The output gate decides what parts of the cell state should be output as the hidden state. These gates work together to control memory manipulation. They determine what to forget from long-term memory, what new information to store, and what to output at each time step. The key insight is that cells retain information across time steps. Gates control how that memory is manipulated, and both the outputs and cell states are passed to the next cell in the sequence. This elegant design allows LSTMs to selectively remember or forget information over very long sequences. Let's examine the forget gate in detail, as it's the first step in the LSTM process. The forget gate decides what information we're going to throw away from the cell state. This decision is made by a sigmoid layer. The gate looks at the previous hidden state H_T1 and the current input X_T, and outputs a number between 0 and 1 for each element in the cell state. A value of 1 means completely keep this information, while a value of 0 means completely get rid of it. Values in between represent partial forgetting. Let me give you a practical example. Consider a language model trying to predict the next word based on all previous words. The cell state might store the gender of the current subject so that correct pronouns can be used. When we encounter a new subject in the sentence, we want to forget the gender of the old subject. The forget gate learns to do exactly this. It will output values close to 0 for the gender information when a new subject appears. The mathematical formula shows that F_T equals sigma of W_F times the concatenation of H_T1 and X_T plus a bias term. Now let's look at the input gate, which determines what new information we store in the cell state. This process has two parts working together. First, a sigmoid layer called the input gate layer decides which values will update. It outputs values between 0 and 1, where 1 means this value should definitely be updated. Second, a ton layer creates a vector of new candidate values, denoted as C_tilde_T, that could potentially be added to the cell state. The ton ensures these values are between -1 and 1. In the next step, we combine these two outputs to create the actual update to the cell state. Going back to our language model example, when we see a new subject in a sentence, we want to add the gender of this new subject to the cell state, replacing the old gender information that the forget gate just removed. The input gate learns to recognize when new important information arrives and should be stored for future use. Now we come to the cell state update, which is where the magic happens. We update the old cell state C_T1 to create the new cell state C_T using a simple but powerful formula. First, we multiply the old cell state by the forget gate output F_T. This drops the information we decided to forget. Then, we add the product of the input gate output I_T and the candidate values C_tilde_T. This adds the new information we decided to store. The formula is C_T equals F_T times C_T1 plus I_T times C_tilde_T. This is the key equation of the LSTM. Notice that the cell state update involves only element-wise multiplication and addition operations. This linear nature is what allows gradients to flow backward through time without vanishing. The cell state acts like a conveyor belt running through the entire sequence, with the gates making small linear modifications along the way. Finally, let's examine the output gate, which determines what we output from the cell. The output is based on our cell state, but it's a filtered version. First, we run a sigmoid layer called the output gate to decide what parts of the cell state we're going to output. This gate considers the previous hidden state and current input. Then, we pass the cell state through a ton function to push values between -1 and 1. Finally, we multiply this ton output by the sigmoid output of the output gate. This gives us only the parts we decided to output. For example, in our language model, if we just saw a subject, we might want to output information relevant to a verb that might come next. The output gate learns what information from the cell state is relevant for the current prediction. The formula is H_T equals O_T times tan of C_T, where O_T is the output gate activation. This hidden state H_T is then used for the prediction at this time step and passed to the next LSTM cell. Let's briefly discuss gated recurrent units, or GRUs, which are a simplified version of LSTMs. GRUs combine the input and forget gates into a single update gate. This reduces the number of parameters and makes the model less computationally demanding while still capturing long-range dependencies. Here's how it works. The update gate decides how much of the information from the past should be kept for future steps. It helps the GRU remember important details. You can think of it as combining what the forget and input gates do in an LSTM. The reset gate decides how much past information should be forgotten. If something is no longer relevant, the reset gate helps forget that part. GRUs have been shown to perform comparably to LSTMs on many tasks, while being faster to train. The choice between LSTM and GRU often depends on your specific application and computational constraints. In practice, LSTMs are often preferred when you need maximum modeling capacity, while GRUs are chosen when training speed is important. Let's summarize the key points about LSTMs. First, the cell state C_T enables long-term memory. It's the highway that carries information through the sequence, allowing the network to remember important context from far back. Second, sigmoid gates control information flow. The forget, input, and output gates work together to determine what to discard, what to store, and what to output at each step. Third, ton activations keep values bounded and stable. This prevents the values in the cell state and hidden state from exploding. Fourth, and most importantly, this carefully designed structure mitigates the vanishing gradient problem. This is what makes LSTMs so effective at learning long-range dependencies in sequential data. LSTMs have revolutionized many fields, including natural language processing, speech recognition, machine translation, and time series prediction. Understanding their architecture is fundamental to working with sequential deep learning. Thank you for your attention. I'm happy to answer any questions you might have.